Welcome back, everybody. So we're gonna finish up 3.5 and then move on to 3.6. We'll move homework for Unit 4 homework until next week after we come back from the exam. As a reminder, exam 3 has been moved not today, but on Monday, Wednesday of this week. It'll cover everything up until the end of this section. 3.6 will not be covered on the exam. Um, so. What else? I have your exam twos graded. I will be handing them back to you at the end of the hour. At which point we can then you will have until next Monday to turn them in. But I don't want you to work on these things. I mean, we can even go into if you need to, we can even wait until Wednesday of next week, in case you need a little extra time to do the redo. Um, but I don't want you working on that right now. I want you studying for the exam that's coming up on Wednesday. So that's the reason why. So anyways, for this one, so going back over this stuff real quick, unless there's any questions about the changes. Exponential equations, they end up in one of three different forms that we're going to see, but this can be generalized. It's either your exponential function has the same base, b to the something equals b to the something else, in which case you set the exponents equal to each other and solve. Or you have that they have two different bases and they're equal to each other, a to the something equals b to the something else, or you get b to a something equals a number. And these were the different ways we did work with it. And the whole goal was that you could utilize the logarithms to remove the bases. So we saw a couple of them here, and we'll get more practice with them. But with this one here, we went through it very, very quickly at the end. So you already have it in the format of something to something equals another base to something else. So there's no common bases. And so what we do is we utilize the natural log because like any logarithm can bring down exponents. But in particular, natural log is faster to write. You could use regular log, the common log, log base 10, that is, if you wanted to, but just ln seems to be the fastest one to write, so it's the best one to choose. And so by doing this, this brings these exponents down. And then even though it doesn't look like it, this is a linear equation. So natural log of 11 is just a number. Natural log of 7 is just a number. So we have two things that have a variable of x. We brought them to one side, and we brought the other thing over to the other side, factored out the x, and solved for x. Now, as you can imagine, plugging this into your calculator to check your work is a very, very daunting task. Trying to fit that into that equation is really, really annoying, whereas using the approximation is much faster to check. But if I use the approximation to check my answer, let's go ahead and do that real quick. So let's see. I'll plug it into the left-hand side. 11 raised to the 6 times negative 1.1423 plus 5. I end up with, on the left-hand side, 0. Don't write this down, but I wrote 0.0117345 on forever. And if I do it with 7 raised to the 2 times negative 1.1423, I end up with 0.011729 . So notice these numbers aren't the same, right? They're not the same. They're off by tens, hundreds, thousands, 10,000, 100,000s. They're off by about honestly 4 millionths. They're only off by that much, but they do look different, and that's only because we're using an approximation. If we plugged in this into the whole thing, if we use that in the exponents for our x value, it would be the exact same number. But the point being is when you plug in these numbers, as long as these numbers look relatively close to each other, you probably did it right. If you want to check your work, that is. So to reiterate, this is the number you use to check your work, but your answers won't be exactly the same. As long as they're relatively close, you probably did it right. Okay? Any questions on that? Now, another thing that you may note is that you could have used log base 7 or log base 11 if you wanted to instead of natural log. It may make things look easier, but it's up to you. So I could have used log base 11 like I did here, because that would allow us to cancel it here, and then we only have one logarithm on the right-hand side, which might look better to you. It takes about the same amount of time to write. Log base 11 of 7 is just a number. So I can bring the two things, the 6x and the 2x log base 11 of 7, over to the left-hand side, equals the constant, and I can solve it that way. It will give me the same number regardless. It's just that log base 11 of 7 is a slightly different number than what I originally have here, but it ends up working out just as well. Same thing with log base 7, but it ends up taking a little longer. That's why I don't typically do it this way. It ends up looking a little bit weirder, but it's your call. If you want to do it that way, you can. Any questions? Okay. Now we'll move on to logarithmic equations. So we did the exponentials. Now it's time to do the logarithmic. So simplify with the help of logarithmic properties. That's unit 3.4 as necessary to get in one of the two forms. Either you get log base b of a blue box equals log base b of a green triangle, or a red triangle, however you want, or you have log base b of a blue box. Oh, sorry, not a red triangle. Not that it really matters. Equals a number. Those are the two formats that it will show up in. You might be wondering, what about log base b equals log base b of blue box equals log base a of a red triangle, where they have two different bases? That is a much more challenging opportunity and requires the change of base theorem along with a lot of not so fun mathematics. So we typically avoid that case. So those are the two formats. If you're in form A, well, then you have log of something equals log of something else. And they have the same base. So by the theorem at the very beginning, of the facts from the very beginning, all that needs to be done is setting the insides equal to each other. So we set blue box equal to red triangle and solve. And that's how you take care of that situation. Because if you have two logarithms with the same base and they're equal to each other, then their insides need to be equal. If you're in the other format, though, the blue box is where all of the variables are hiding. And you might remember that if you were to convert this to exponential form, b raised to the number, that'll be a number, right? If this was 2 and this was 2, this would be 2 to the second power. So it'd be a number equals the variable stuff. So you're going to convert to exponential form. And solve. And don't worry, we will get several practice problems of each of these things, and that will help us with all of it. So convert it to exponential form. Whew. Now, solving logarithmic equations, as we mentioned at the very beginning, logarithms have problems. They can't have negative numbers or 0 inside of them. We saw that in the previous section. We saw that we were reminded of it here. You cannot plug in 0 or negative numbers into logarithms. And so sometimes when you get answers, they may be ones that work, but like work in the later version, but not in the original, which is called an extraneous solution. Now, to be clear, it is okay for your variables, your answers, to be negative. That is not wrong. It's just when they get plugged into the equation, the original equation, you can't have negative numbers on the inside of the logarithm. So x equals -2 is a completely valid answer. It's just when you plug it in, it can't give a negative number. You'll see in a second. So for this one, solve the following equation. Log of x plus log of x minus 3 is equal to log of 5x minus 7. Okay. So step 1 is to get it into the proper format. And I'm going to rewrite it so it's log of x. And then I'm going to overemphasize the plus in between for a reason you'll see in a second, if you don't already, is equal to log of 5x minus 7. Now, in its current format, it does not look like log of something equals log of something else. However, we can combine logarithms, right? We learned how to condense logarithms in 3.4. Specifically, that if you have the addition on the outside, that becomes multiplication on the inside. So this actually becomes, leave a little bit of space actually. So write it down a little bit further. Log of x times x minus 3 is equal to log of 5x minus 7. Addition on the outside of logarithms becomes multiplication on the inside of a logarithm. And x times x minus 3, well, that's going to be x squared minus 3x. So now we have it in the format of log base 10, because it's common log, equals the same log, common log, of something else. So we are in form A. So we will set we'll set the insides equal to each other. So that's step 2. We have x squared minus 3x is equal to 5x minus 7. So that is a polynomial equation. In particular, it's a quadratic equation. We can bring it. We need to bring everything to one side, factor, and find the solutions. So we'll subtract the 5x and add the 7 to both sides and get x squared minus 8x plus 7 is equal to 0. Well, that factors nicely to x minus 1 times x minus 7 equals 0. And so, and you can use whatever methods you want to factor. And so, setting this equal to 0 means you're going to use the zero product rule to set each factor equal to 0. And this time, instead of writing x equals, I'm going to say the possible solutions are x equals 1 and 7. And if you've looked back, if you look back over all of our notes, whenever we're talking about a procedure to solve a type of an equation, you'll always notice that I say like the last step is optional step 4 or whatever to check your work. This one, it doesn't say optional because it is not optional to it's not optional to check the work. You have to check it. These might work, they might not. So, step 3 is to check our work. So, if x is equal to 1, we'll plug it in, log of 1 plus log of 1 minus 3. Does that equal log of 5 times 1 minus 7? Now, I could go through into my calculator and plug these things in, but I don't need to. Let people write that down before I continue onwards. All I'm looking for is to make sure that all of the logarithms are well defined. Do any of the logarithms, the 3 logarithms present, do any of them have negative numbers on the inside? Yeah. The second and the third. This one and this one are going to cause issues. If you try and plug it into your calculator, even that's the good news. Check the left-hand side, plug into your calculator log of 1 plus log of 1 minus 3 or log of -2. Your calculator will say math error. And that's because logarithms for negative numbers don't exist. So the good news is you don't have to know it as long as you check your work. You don't have to understand it, but you should. The whole thing. So let's think about why that is the case. So this one is out of the question. And let's then check x equals 7. Well, log of 7 plus log of 7 minus 3, does that equal log of 5 times 7 minus 7? And it will work out. Let you write it down, and then we'll talk about it. How do I know that they do equal each other? Because I'm confident in my algebra. And as long as I'm confident in my algebra and the insides of all the logarithms present don't result in negative numbers, it's probably going to work out. You can go through and plug it into your calculator, plug in log of 7 plus log of 4, write down what you get, and then plug it into the right-hand side and plug in what you get. And you should get, see here, on either side, you should get log 7 plus log 10. Or you should get 1.44-ish on each side. But the main thing that I'm looking for is make sure that the insides aren't negative numbers. 7, not a negative number. 7 minus 3, positive 4, not a negative number. 5 times 7 minus 7, that's 28, not a negative number. So I'm good. So as long as the insides are positive, I can be certain that I got it correct. Now, why does that happen? Why is it that one doesn't work, despite it being a solution that we saw from step 2? Well, it's because when you combine logarithms, you change their domain, which is kind of interesting. Case in point. I'm going to add in a page just for a second so you can see it. You don't need to worry about it too much. You don't need to draw this. It's just for us. X minus 3, right? Versus log of x times x minus 3. So, if you're thinking about these as functions, right? This function on the left, here you need x strictly greater than 0, and this means x needs to be strictly greater than 3. That's just by definition, right? The log of x is only well-defined as long as x is strictly greater than 0, and log of x minus 3 is only defined if x minus 3 is strictly greater than 0, which simplifies to x is strictly greater than 3. So, taking both of them into account, we need both of those things to be true. And so that requires that x needs to be strictly greater than 3. If you need help visualizing that, just imagine a number line. Here's 0, here's 3. The green implies that we need to be all the way to the right of 0, and the blue implies that we need to be all the way to the right of 3. Since the blue version isn't defined over here, we have to get rid of it. Once again, let me show that again. This piece can't be negative. Even though at 1 or at 2 or at 2.5, the green portion is positive, the blue portion is going to be negative. So this spot actually has to be cut out. So that's one thing about it. Versus this one, its domain, if you solve x times x minus 3, so that's, by the way, that's the interval 3 to positive infinity. If you solve this inequality, that's a nonlinear inequality, right? And that has a solution of negative infinity to 0 union 3 to positive infinity. So when you combine logarithms, you fundamentally change them. When you combine them together, they end up getting warped a little bit because you can plug in two negative numbers and have it result in a positive number. By themselves, I can't plug in -4 because then they'll both be negative. But if I plug it in here, -4 works because it'll be -4 times -7, which results in positive 28. So when you combine, like in short, when you combine two logarithms together, you change their domain. That's why you need to check in the original equation. That's the reason why it happens. Any questions on that? Okay. So you have to check your answers with logarithms because of how they work. Another one. We got solve the following equation. 3 log base 2 of x squared minus 5x minus 6 plus 7 is equal to 16. So first and foremost, we need to start simplifying it. So we've got, that's step 1. We've got 3 log base 2 of x squared minus 5x minus 6 plus 7 is equal to 16. What I need to do is I need to subtract 7 from both sides. I end up with 3 log base 2 of x squared minus 5x minus 6 is equal to 9. And then I'll divide by 3 to get that log base 2 of x squared minus 5x minus 6 is equal to 3. So from here, unless there's any questions on any of the algebra that I've done so far, it's in the format of log of something equals a number. So the intuition as to why I'm doing what I'm doing is I need to solve for x. X is on the inside of the logarithm. If I convert to exponential form, that inside becomes free of anything. So that's what step 2 is going to do. I'm going to start at the base, work my way across the equal sign, and then back over to get myself 2 to the third power is equal to x squared minus 5x minus 6. Oh, I forgot to finish that problem, the previous problem. So we'll finish this one. Let's finish this one up, and then we'll go back to that previous one for just a moment. Okay. So 2 cubed is 8. So we end up with 0 is equal to x squared minus 5x minus 14. And that should factor. And if we don't want to factor, we can always use the quadratic formula, right? Use that to our advantage. But ends up being 0 is equal to x minus 7 times x plus 2, which gives me the possible solutions. X equals 7 and negative 2. Step 3 is to check my answers. Now, I didn't actually end up changing any, I didn't end up combining or moving any logarithms. So honestly, these probably should end up being both solutions, but we should still check. I say that from years of experience to notice that since I didn't combine any logarithms, they probably will end up working, but that's not a guarantee, so it's always worth a shot to check. And we're going to check in our head. If x is equal to 7, it ends up working. And if x is equal to negative 2, it ends up working. Now, what you're supposed to be doing in your head is, once again, checking to make sure that when you, as long as you're confident in your algebra that you did to factor and solve, as long as you're confident in that, all you need to do is just make sure that when I plug in 7 into the logarithms, I get a positive number. When I plug in negative 2 into the logarithms, do I get a positive number? And so, just for the, to see it, if I plug in 7, I'm going to get 49 minus 35 minus 6, because it's going to be 7 squared minus 5 times 7, which is 35, minus 6. And that equals, the inside of the logarithm will equal, that's 8, right? Let's see here. Because it's going to be 14. Yeah, you get 8. Good, it works. The inside of the logarithm is a positive number. It works out. Excellent. If I plug in negative 2, negative 2 squared is positive 4 minus negative 10, so plus 10 minus 6. That also equals 8. So that's what I'm doing in my calculator or in my head. I'm plugging in the 7 into any logarithm that I see and making sure the inside is strictly positive. So this ends up being the answer. Both of them are correct. Marlene. That's correct. Because I'm trying to plug it into the logarithms. Please, yes.
All right.
Yes, you can. If you don't want to sit down and factor it, you can use the quadratic equation. Yes.
If the plugins equal a positive, is it possible that they won't equal the same value?
If you made a mistake in your algebra, yes. But if, as long as your algebra is correct, as long as you get positive numbers, it will work. Yeah. Yeah. Yes, as long as the inside of every logarithm is a positive number, it will be the answer. That is enough to check it. If you want to be super careful, you can definitely actually plug it in and make sure you get the same thing on both sides. Absolutely. But it's not necessary as long as you've checked to make sure that the inside of the logarithms are positive. Back to the previous one for a moment. So we saw that 1 didn't work, but 7 did. So my way of writing the answer is to write x equals 7 only. That is the way I will write it. So if you're looking at the exam 3 review guide and you look at the answer keys, you might see a couple situations where it says like x equals 2 only or x equals 7 only. That's my way of telling you that there were multiple options, but only one of them worked or only two of them worked. Or whatever it may be. Now, on an exam, if you don't want to rewrite it, I've had plenty of students do this instead. So I'm just going to move this for a second. Plenty of students, what they'll do is they'll just cross out the 1 and then they'll box their answer like this. And that's fine with me. If you cross out the one that doesn't work and box it in, that's okay. That works for me too. I just like writing it that way. Is that okay? Any questions on those? Okay, looking at what we've got those two things. Okay. Let's go ahead and we'll do A and B together, and then I want you guys to do C. A because it has two ways of looking at it. So right now it's natural log of y minus 4 is equal to natural log of y plus 6 minus natural log of y. Now there are two methodologies on how to solve this. Option 1. Is the straightforward idea. So this is the one that I would expect students to do if they were not trying to be clever at all on an exam, which is probably what's going to happen, right? If we're on an exam and we're trying to solve these types of things, we don't really want to be clever. We're just trying to find the answers. So you look at this and say, okay, well, on the right-hand side, there's a subtraction. I can convert that. So I'll rewrite it. Natural log of y minus 4 is equal to natural log of y plus 6 minus natural log of y. Well, if I do that, subtraction on the outside becomes division on the inside. That's one of the other properties of logarithms. If you want to condense them, anything that is negative or subtracted goes into a denominator. Anything that's positive or added goes into a numerator. So we can do that. We can write this as natural log of y minus 4 is equal to natural log of y plus 6 divided by y. And if we do that, now we have log of something, natural log of something equals natural log of something else. So we're in form A, where we have two logarithms equal to each other. That means that their insides are equal to each other. That means that y minus 4 is equal to y plus 6 over y. Now that's a rational equation. How do we solve rational equations? And it's okay if you don't remember it. There's an intuitive idea on what we want to do. What should we do to solve this equation? Multiply by the denominator. We don't want to deal with a denominator. We don't want to deal with fractions if we can avoid it. So we'll multiply both sides by y. And it cancels it. And we end up with y squared minus 4y equals y plus 6. That gives me y squared minus 5y minus 6 is equal to 0, which factors to y minus 6 times y plus 1 is equal to 0, which gives me y equals 6 and negative 1. Again, you need to make sure you're practicing your factoring skills. That's never going to go away. Or figuring out how to solve them. Like knowing your quadratic formula is another option. I would recommend knowing your factorization because that really helps with calculus. But you don't have to. There are ways around factoring in calculus. There are a few ways. Now, those are the possible solutions. So, does 6 work? If I plug in 6 into the original equation, 6 minus 4, that's a positive number. That's okay. 6 plus 6, that's 12. That's a positive number. That's okay. Natural log of 6, that's a positive number. That's okay. So 6 works. Now let's try -1. -1 minus 4, that's a -5. That doesn't work. So -1 is out. So it's going to be y equals 6 only. Or you can just cross it out and write y equals, and just box it in with the crossed out 1, -1. So that is the way to do it, but like requires you to remember how to deal with rational functions, excuse me. Which is not the end of the world. We can still survive, right? It's okay. So that's how you do it if you were on an exam scenario and you didn't know to be clever. Here's a way to do it while being clever. Unless there's any questions on that first option. So if you wanted to instead, oh, Louis, yeah.
So the second option, the last step, we're supposed to multiply the denominator to get rid of it.
Yes. With this option, we want to multiply by the denominator to cancel it on the right-hand side to give us a truly polynomial equation. It's a nice, neat polynomial equation. Now with option 2, one thing you might notice is that we can always add or subtract things from both sides of an equation. So what we could do is we could take this natural log of y minus 4 equals natural log of y plus 6 minus natural log of y, and we could add natural log of y to both sides to cancel it on the left, or on the right, excuse me. That would give us, instead, natural log of y minus 4 plus natural log of y equals natural log of y plus 6. And from here, we have a plus now on the outside. We have addition on the outside, which becomes multiplication on the inside. So this becomes natural log of y minus 4 parentheses times y equals natural log of y plus 6. But that means now we have natural log of something equals natural log of something else. We set the insides equal to each other. We get y squared minus 4y equals y plus 6, ... and so on. It ends up being the exact same equation. Test something out. So it's the exact same thing. It's just a different way to do it. You end up having to solve the exact same equation at the end of the day. It's just a matter of how you want to look at it. Either you can look at it as addition, the option 2, or you can look at it as division, subtraction converting into division as an option 1. And if that bled over into example B, that's okay, because example B is actually going to be very quick. Are there any questions on that? Okay, so example B is an exponential equation and doesn't involve logarithms. So we need to get it into the format, one of the 3 formats, either base B of something equals base B of something else, or base B of something equals A, base A of something else, or base B of something equals a number. And so what we'll do is we'll subtract 7 from both sides. We end up with 12 to the x minus 2 is equal to negative 2. And right here, I can already tell you what the answer is going to be. Does anybody know what the answer is going to be? No solution. Victor's absolutely correct. So we can stop here. Exponential functions are always positive. So 12 to the x minus 2 can't equal negative 2. Twelve to the x minus 2, no matter what x is, be it negative 5,000 or 7,205. No matter what x value you plug in, 12 to the x minus 2 is always going to result in a positive number, strictly positive number. It might be really close to 0, or it might be incredibly large, but it's always positive. So there's no way for it to equal negative 2 in the first place. Now, if you don't recognize that off the bat, that's okay. You can still try and do the whole kit and caboodle. You can still try and apply natural, just watch what happens. If I apply log base 12, I get log base 12 of the left-hand side equals log base 12 of the right-hand side. So log base 12 of 12 to the x minus 2 equals log base 12 of negative 2, and this doesn't exist. So there's no solution. So if you are on an exam, if this were to show up and you were immediately right here and you wrote that there is no solution, you would get full credit. You don't need to explain anymore. But that's not the end of the world. If you don't recognize that, you can still, if you remember the procedure, you can still try and use it, and you'll see that it doesn't work out. Because as soon as you try and find log base 12 of negative 2, you'll find that it doesn't exist. Your calculator will say math error, and you'll have a not so good time. Well, that's not true. It's not going to be a bad time. It's just going to be a quick time for me. You're going to be done. You don't need to do anymore. Any questions on that? I bring this one up because it's an important thing to understand is that exponential functions are defined, they only produce positive numbers. They are never equal to 0. They are never negative. And we'll move on to the next one. 8 minus 5e to the x plus 15 equals 2. How should I solve it? I need to get the variable by itself. It's an exponential equation, so I should subtract 8 first. I end up with negative 5e to the x plus 15 is equal to negative 6. At which point I'll divide both sides by negative 5. I end up with e to the x plus 15 is equal to 6/5. Now what do I do? Multiply by the denominator, multiply by 5. Unfortunately, that will just bring me back to over here. So instead, I have to realize what I want to do. I want to get this x plus 15. I'm trying to solve for x. I want to get the x plus 15 out of an exponent. I want to get it out of the top point. So I can utilize logarithms to do that. I'm going to apply ln in this case, log base e. Now I'm going to write something wrong on the right-hand side here that some students write. And I want you to tell me what's wrong. Is it 1, 2, 3, or 4 that's wrong? 3 and 4. The thing is, a natural logarithm needs to be applied to something. This right here makes no sense. It's nonsense. Because natural log is an operation on something. It would be the same thing as me writing this. That doesn't make any sense because you're asking yourself square root of what? What, well, like square root of what? Same thing here, natural log of what? There's nothing to the right of the natural log. And that's just, you're putting a period before the end of your sentence if you do it that way. So when you write it, you have to write natural log of the left-hand side equals natural log of the right-hand side. That is natural log of e to the x plus 15 equals natural log of 6/5. Like that. And as I said before, you can squeeze it in if you want. You don't have to be perfect. You can write ln like this and ln like that. You can do that. Even if it's really, really, really tiny, it's okay. As long as it's made sure that it is mathematically valid. I could not care less. The reason we have done this is natural log is log base e. So we have log base e of e to the something. They cancel each other out. And so what I end up with is x plus 15 is equal to natural log of 6/5. I'll subtract 15 from both sides to solve for x at the end of the day. X is equal to natural log of 6/5 minus 15, which is approximately negative 14.8177. I'd prefer the answer in exact form, which is the natural log of 6/5 minus 15, but I know Alex wants you to write it as a decimal approximation. On an exam, I am fine either way because of this. Any questions on that? Yes. And then
So, ln gets 15, the 6/5 and the natural log of n is not correct.
sorry, say that one more time.
So for the question, the natural log of n, x plus 15 equals 6/5 now. The right one is correct?
This right here?
Yeah.
That's correct now because it's natural log of something. Natural log needs to be on the left when you're writing it. Okay? And Victor.
I think it would take longer, but is it possible to do the conv log and then take the power rule?
Yes, you can, but it's going to take longer. Yeah. You can use common log, because then the e and the log don't cancel. And so it'll end if you decide to use log instead, just like this is a good point. If you use log instead, so log of the right-hand side equals log of the left-hand side, that is log of e to the x plus 15 equals log of 6/5. What ends up happening is the exponent can be brought out front, but log of e does not cancel. So we end up with x plus 15 times log of e equals log of 6/5, which we have two ways we could go about solving this. Just like if we had x plus 15 times 3 equals 6/5, we could either distribute the 3 in and then solve for x, or we could divide by 3 right from the get-go. We could go like this, right? And that would cancel it on the left-hand side. We could do that and that would be faster. Regardless of how we do it, we can solve this in that way, in that fashion. I would recommend dividing both sides by log of e. And what that ends up with is x plus 15 equals log of 6/5 over log of e, which gives me, oh, there's a 15, not a 5. And that gives me x equals log of 6/5 over log of e minus 15, which if you plug that into your calculator, it'll be the exact same decimal number. And it has to do with something that we didn't really get to talk about, the change of base theorem, the reason why those things are equal. But it ends up being the same value. So that is another way to do it if you don't want to use natural log, but I would encourage it because it takes way less time. Okay. Any other questions? All right. Let's take our break. We'll come back at 101 and we'll get started with the rest of them. Uh, and then we'll come back. So let's come back at 101. People watching the recording, go stretch and get some fresh air. All right. So I've got 4 more examples up here of logarithmic and exponential equations. I would like us to go ahead and start working through them. I'll slowly fill in details, but you should be trying to work through them yourselves. I will slowly fill in the details. People watching the recording, pause it and start working through it yourself. If you get stumped, look, unpause it. I have there, it's for part C as well, if you'd like to check your work. Okay, we're gonna go through all of them. Don't worry if you don't have the last ones written down, we'll get to it. So with this first one, so it is a logarithmic equation because it involves logarithms. And at its current stage, there is no way to get it into the proper format because there's no way to get the log of something equals log of something else. There is a way to bypass it with this. There's a silly thing that you can do is you can rewrite 2 as what is it? What is it? You can write it as log base 4 of 4 squared. You can do that. That technically is a trick that you can do because remember, log base 4 of 4 to something, the 4 and base 4 cancel. And that way you can combine on the right-hand side, but that's not what I saw. Um, what I decided to do is subtract log base 4 of x minus 3 from both sides. Doing so allows me to combine those two logarithms into a singular logarithm with division on the inside. And then I've got log of something equals a number. So I can convert it to exponential form. The reason I would want to do that is that allows the logarithm to go away. That allows the logarithm to get removed. And so now I have 4, starting at the base, moving across the equal sign and then back over. I've got 4 raised to the second power is equal to 2x over x minus 3. That is once again a linear equation, or that is a rational equation, which we don't want to deal with the fractions. So we'll multiply both sides by x minus 3. Doing so gives me 4 squared, which is 16. So it gives me 16x minus 48 is equal to 2x. Subtract 2x from both sides, add 48 to both sides to get 14x equals 48. And divide both sides by 14, which reduces down to x equaling 24/7. Now that's about 3 point something-ish. So if you plug it into both sides of this equation, you'll see that it works. That's why there's a green check mark here, is I checked it in my head. 2 times positive 24/7, that's going to be positive. 24/7 minus 3, if you can't see that at the top of your head, that's understandable. Plug it into your calculator, you'll see that you get a positive number, so it should be all good. Next one has a 2 attached to the logarithm. So you can combine the right-hand side, but the problem is that 2 can't, you have to have log of something equals log of something else. So I've actually given this type of problem on an exam before, and my students would get stumped right here. So the thing is, we can't set them equal to each other yet because it's not log of something equals log of something else. Right now, it was 2 log of something equals log of something else. But by the properties of logarithms, coefficients on the outside become exponents on the inside. So it's log of x plus 2 quantity squared is equal to log of x plus 10 times 4, which is really log of x squared plus 4x plus 4 equals log of 4x plus 40. They're the same base logarithm, so they can equal each other. So you set the insides equal to each other. Bring everything to one side, you get x squared minus 36, which is a difference of squares. So we factor it, x plus 6 times x minus 6. That gives me 2 different possible solutions, -6 and +6. But if you plug in -6 into this, you get a negative number, which does not work. It works here, -6 works in the right-hand side, but that's not enough. It needs to work everywhere. So -6 is out, but +6 works, which gives us x equals 6 only. Which once again, you can just box your answer here if you'd like. That's fine too. As long as you've crossed out the wrong answer, the extraneous solution. The next one is definitely the most time intensive, and it is because it's one of the ones where there is no common base. We have 3x plus 6 equals 5 to 2x minus 1. 3 and 5 don't share any common bases, so we have to use the natural log or common log. It's your choice. Natural log is faster to write. That's why I use it. And doing so allows us to bring the the exponents out. So we got x plus 6 times natural log of 3 equals 2x minus 1 times the natural log of 5. Now, just remember that natural log of 3 and natural log of 5 are just numbers, so they can get distributed in. So distributing it into the x gives me natural log of 3 times x on the outside, plus 6 natural log of 3. However you want to write it, you can write it as natural log of 3 times 6, it doesn't matter. Equals 2x natural log of 5, or 2 natural log of 5x, doesn't matter, minus natural log of 5. Now from here, I have to realize that that is a linear equation. It doesn't look like a linear equation by what we're used to seeing, but it is. Because 2 natural log of 5 is just a constant on an x. It's a coefficient on an x. Natural log of 3 is just a coefficient on an x. 6 natural log of 3 and negative natural log of 5, they're just numbers. So I bring the numbers to one side, the x terms to the other, and that allows me to factor out an x. I've got x times natural log of 3 minus 2 natural log of 5 is equal to negative natural log of 5 minus 6 natural log of 3. You could have brought the x terms to the right if you wanted to, and bring the non-x terms to the left. That works as well. It's your choice. If you would preferred that, like you could have subtracted this to this side and added natural log of 5 to both sides. It would work either way. Your answer would just look slightly different than mine, but it would be still correct. And then we divide both sides by natural log of 3 minus 2 natural log of 5 to get our answer, which is that x is equal to negative natural log of 5 minus 6 natural log of 3 over natural log of 3 minus 2 natural log of 5, which is approximately, if you use your calculator, 3.8680. Any questions on that? Now, if you decide to check your work, by the way, just once again to reiterate the fact that it's really, really difficult to plug this into your calculator in the exponents. Like, I mean, writing this in your calculator, 3 arrow parentheses, negative ln of 5 minus 6 ln of 3, end parentheses, divided by, it's a lot of work. It's not worth it. So instead, you plug in the 3.8680 into your calculator. If you do that, on the left-hand side, you would get 51,077.84214, and you plug it into the right-hand side, you get 51,081.30092, dot, dot, dot. So these numbers are not the same, right? They're off by a few digits, but it's only because this is an approximation. These are very close to the same number. So yes, they are substantially off, but that's only because, remember, these are exponential functions. And exponential functions, they grow very, very quickly, right? 3 squared is 9. 3 to the 4th is 81. So, and then 3 to the 5th, from 81, then it goes to 243. So it jumps up very quick as you get further and further out. So each decimal point starts to make a dramatic impact as you move further and further away from the from 0. So that's why it doesn't look like it's the same, but that is close enough for you to be certain. If you want to be extra certain, instead of using your approximation, use the whole decimal expansion that your calculator gives you, and those will basically be virtually identical. Either way. Last one, we have 9 to the 4x minus 5 equals 1/27th to the x. They have a common base of 3. That's what I noticed. However, you can still get by without doing that, and I'll show that on the next, I'll add a page and show that. Just in case this was on the exam and you didn't see it at first. But we'll first go over the fast way, and then we'll go over the long way. So 9 and 27, I saw those numbers, and I know my powers of 3s. And I promise you on an exam, I'm not going to bust out random ones. I'm not going to make you do 343, which is 7 cubed. I wouldn't expect us to know that. Or let's think of a different one. 100 and I don't even know what 14 squared is off the top of my head. 196. I'm not going to bust that out on this thing. Okay. So Just be looking for those ones. If it's not one of the quick ones that you can check, then move to the other options. But 9 and 27, they're common bases of 3. 9 is 3 squared. So this is 3 squared to the 4x minus 5 equals 3 to the negative 3 because it's 1 over 27 to the x. Power raised to a power, you multiply the powers together. So that's why it's 3 to the 8x minus 10 equals 3 to the negative 3x. And from here, we have two things with the same base. That means that their exponents have to be equal to each other. There's no other way for these two things to work. So 8x minus 10 is equal to negative 3x, which you can solve and get x is equal to 10 elevenths. Now, if you did not notice that, you might have been like, okay, well, what I could do, so I've got 9 to the 4x minus 5 equals, leave some space, 1/27th to the x. You could either apply you could apply natural log, or you could apply log base 9. It's your call. I'm going to apply natural log to both sides. And that allows me to bring the exponents down. I've got 4x minus 5 natural log of 9 is equal to x times natural log of 1/27th. I have to distribute the natural log of 9 into both. I get 4 natural log of 9 times x minus 5 natural log of 9 equals x natural log of 1/27th. And then it's your call. Either you bring all the x terms to the right, or you bring all the x terms to the left and the constant terms to the other side. I'm going to bring all the x terms to the left just because it feels better to me. So I'm going to bring that over, and I've got 4 natural log of 9x minus x natural log of 1/27th is equal to 5 natural log of 9. And on the left-hand side, there's a common factor of x. So I can factor that out and divide by it. I get x is equal to 5 natural log of 9 divided by 4 natural log of 9 minus natural log of 1/27th. And if you plug that into your calculator, fun fact, so if I do that, 5 natural log of 9 divided by 4 natural log of 9 minus natural log of 1/27, my calculator gives me 0.909090 repeating, which is 10 elevenths. You can even, like, if you have my calculator, you can even press the S to D button when you do that, and it'll show you that it ends up being 10 elevenths as well. That being said, if you didn't do that and you just wrote down the approximation for that, I'd give you full credit. I'd give you full credit. And then I might do what my TA did in Calc 3 at one point and say, did you even look for common bases? Question mark. Because this is a lot more work than you needed to show, right? There was a problem on my Calc 3 exam where I couldn't figure it out until the last 3 minutes of the class and the last 3 minutes of the exam. And I frantically started writing it down. And there was a quick way, which involves a thing that we do in Calc 3 called polar coordinates. If you converted it to polar coordinates, it would have been way faster. It would have taken half a page. But I had to do something that I did it a different way using integration by parts. And so it took up the entire page. It went from being a problem that only took this much work on a page, or like it went from taking this much work to the whole page. And I wrote it in 3 seconds. I had a rug burn on my pinky, and my TA gave me full credit and said, "Did you even try polar?" Because he had to check all the work, and he was kind of a little bit peeved about it, understandably so. Okay. Seeing as we only have 15 minutes left, and there's no way I'm getting through all of 3.6, we're just going to cancel 3.6. Yay, 3.6 is no longer covered. I'll give everyone a 10 out of 10 on 3.6, so don't worry about that material at all. And it's not going to be tested upon on the final exam either, so we don't need to worry about it, okay? I'm going to go ahead and pause the recording and turn out all the graded exams. So I just handed back the exams. Please make sure that everything looks correct on them. Please make sure that everything graded on them is fairly graded. If you feel like anything was graded unfairly, you can always come talk to me. Worst case scenario is I say no and I give an explanation why I won't give the extra credit, the credit back. Best case scenario is I say, yeah, that's actually a good point. I'll give you full credit back, or I'll give you partial credit back, or something like that. Yeah, I am not perfect. I make mistakes. So if anything like that happens, let me know. Please make sure that all the numbers have been transferred to the front correctly as well. Any of those things, as long as as long as you're supposed to get a higher score, don't let me know. If it's a lower score than you're supposed to deserve a lower score, don't let me know about that one. I gotta say, on the question zero, the algebra question, we're still having a lot of trouble. Some of us are still having a lot of trouble on our factoring and our simplification. That needs to get solved now. Not tomorrow, not after next class. It needs to be now. That is going to be central to everything. So not being able to do your algebra skills, there's like exam 3 will have some algebra skills on there again, just like before. Sorry, not exam 3, exam 3, exam 3. Exam 3 will have algebra questions just like before. The final exam does not. The final exam is the same exam that Math Regular 126 gets, because we have to collect data to make sure that the courses are aligning correctly and looking at the different ways and how to improve both courses and make sure that they are equitable and fixable and getting all the attention that they need to get corrected. 126 is a beast of a course, in case we haven't already seen that. 6 credits is not for the faint of heart. But regardless, exam 3 will have some algebra problems again, just like before, factoring, solving equations, and all that jazz. But the final exam does not. So you've got your your exams back. Because we have the exam on Wednesday, and I don't want you working on the exam redo until after that, I'm going to give you guys until next Wednesday to turn in the exam redos. I will do everything in my power since we're taking our exam on Wednesday. I'm going to do everything in my power to get the exams back to you on Monday of the following week. So next week. So if I give it to you on Monday of next week, if I hand it back to you then, you have until next Monday, so the day of the final, to turn in the review. Furthermore, does anybody questions? Furthermore, I am going to, after Wednesday, after the exam, because I want to make sure you're only doing the homework right now that is present and necessary for the exam. After Wednesday, I will be reopening up all homeworks. So all homeworks will be reopened and you can do them. The due dates will all be, I'm going to give everyone extensions until the 10th of May, which is the Sunday before finals week. So if you want to use those to get a little bit of a boost up in your homework score, perfect. I want you guys to study. And if doing your homework makes you study, then perfect, So excellent. But yeah, and if I forget to on Wednesday, it's possible. I have the memory of a goldfish sometimes. So if they're not extended at that point, just send me a polite email and I'll make sure to do it. But otherwise, as a reminder, 3.6 is not covered. And then looking at the exam, one thing I noticed was question 9. It's 2 options, doesn't it? Does anybody want to ask a question about that in terms of maybe some extra credit? Does anyone want to advocate for themselves? Hey, Phil, can we get some extra credit if we do the other option? Perfect. Great question, Victor. And I'm glad that somebody asked. How many points of extra credit are we thinking? 3? 5? 8? How generous? Going into the final, let's go with 5. Let's go with 5 points of extra credit. So that means you can get up to 50% of the points back plus an additional 5. So just as a note about like calculations, let's just say for the sake of an argument, you got a 40. Then half of that's 60 points that you lost out on. So you can get 30 points back. You can go from a 40 to a 75. You can go from a 30 to a, so that would be 70.60. You can go from 30 to a 70. So you can go from a 30 to a passing C. Because remember, in my class, a 70% is a C in my class, meaning that you pass this course and go on. All right. So there's plenty of opportunities to learn from that mistake and get better. So you can do the other option for up to 5 points of extra credit. All right. Any questions before we leave for today? All right. You could, oh, Marlene, yes. On this coming Wednesday.
Oh, this.
Yes. The 10th of, yeah, which is the day before the final. All right. Cool. All right, guys. Have a great rest of your day. Happy studying. Please make sure you're using the review to help you aid in your study. If there, I can't remember off the top of my head, if there are any questions that are word problems, ignore those. There will be no word problems on the exam. Okay. Otherwise, have a great rest of your day and a great Tuesday, and I'll see you on Wednesday for the exam.